Thanks, Jane, for the introduction. Thanks for being here, and thanks for having the opportunity to present here. My name is Florian Kehl. I'm a PhD student at ETH in Zurich, but I'm pursuing my PhD externally at CSM and Optics Walzes. That's correct, as you mentioned. So we've seen yesterday the presentation of Stéphane Follonnet, and also this morning very nice presentations, the two of Luca and Rita. So I don't really need to explain again the other project in detail, but I just want to focus in my presentation on the tasks mainly of CSM and Optics Walzes. So besides the coordination, also the development of the label-free biosensor module, so like the physical module to detect these EDCs, and the development of the automated sample preparation unit, which is another part of the development at CSM. But I'm not going to talk about the sample preparation unit because I was part of a different PhD thesis of Sarah Oeb, but my part was the detection unit, so to actually detect these compounds. And the goal was to get the detection unit, which is a label-free system, which is highly sensitive, fairly low cost and affordable, relatively low power, versatile, so it could also be used for other things in biotechnology or pharmaceutical industry. Autonomous, compact size, and robust. We can also do the measurements in the field, for example. I'm giving just a broad overview, the concept, because everyone here is from different fields and areas. So I just want to say what's actually the benefit of having a label-free system. Of course, it's label-free, so though we don't have to put a label on the molecules that we want to detect, as yesterday, for example, with these fluorescent assays. So there's no additional labor, no additional costs. The binding sites and also the molecules that we want to detect are unaltered, which with the fluorescent eye might cause some spherical hindrance and so on. But especially, as Luca also mentioned, we can also search for unknown targets. So whatever is binding to our binding site could actually be something which is harmful. And how do we detect it now label-free? It's also a very general picture here. It's a refractometric sensor, and to explain the concept, I would quickly explain the concept of total internal reflection. So maybe some of you have been snorkeling and scuba diving, and you realize when you look up to the surface of the water that it's like a mirror, so it's reflecting the light. And that's always the case if you're in a higher refractive, so an optical, more dense medium, and on top there's a lower, less dense medium on top. You have, at a certain angle, you have total internal reflection, so the light is not passing through the surface anymore, but it's reflected. So now you can think of when we change the refractive index of the top layer, this critical, so-called critical angle changes. And this concept is also used in optical waveguides, as it's commonly used in telecommunication and to guide light over long distances in fibers. So just by several reflectance. So if you sandwich a high refractive index layer between two lower refractive index layers, the light will be bouncing off within this layer. We are also using now this concept for our waveguide, a planar waveguide, and there's different means to couple light into such a waveguide structure. One which is quite favorable also in this perspective is a grating coupler. So not to couple light, let's say, from the side or by a fiber into the waveguide, but by means of a diffractive grating. So here we have a planar structure with a substrate, a high refractive index layer on top of it, and a cover layer. And these gratings are just surface corrugations which allow you to couple light into the waveguide at a certain wavelength and a certain angle. Going into more detail here. So this so-called coupling condition, so if light is actually allowed to be coupling into the waveguide, depends of course on the grating structure itself, on the thickness of the waveguide, and so on, also on the wavelength of the light, but it also mainly depends on the refractive index of these layers, so and also on the refractive index of the top layer. And if this refractive index layer of the top layer, for example, changes, it's again changing the angle of the incident light, or at which angle the light is coupled into the waveguide. Here's an example of the picture. So you have the impinging beam on the grating, and you see the light which is coupled into the waveguide and propagating. So how can we use that as a sensor? So you've seen that the cover refractive index has an influence on this coupling angle. So this is an example of our chip that we're using. So we have these 8 measurement spots. These spots are the actual coupling gratings on the chip. And if you look at the chip from the side view, schematic side view, a slice through it, so it's again the substrate, which is just normal glass, then a high refractive index layer, which is made out of tantalum pentoxide, which is structured with this grating in the half a wavelength period. And on top, we have our aqueous solution, which is as the cover layer, which is again low refractive. And then we immobilize our molecules, our receptors on the surface, and their analytes are binding to the sensor surface. We're illuminating the structure from down here, and then light will couple into the waveguide at a certain angle and couple out of the waveguide onto a detector. But now we're constantly interrogating this angle of incidence. So how do we do that? In our sensor system, there's a laser source, a coherent source, impinging onto a small MEMS micromirror, which is oscillating and scanning the angle around at 1 kilohertz. Then we have the optical system, and over here, that's actually again the grating. So when we tune here the angle, we're constantly changing the angle of incidence over here. And what we then get when the light couples into the waveguide, out of the waveguide, it's this detuning function, so of the coupling angle. So what we see when we constantly sweep back and forth the angle, it's this signal of the outcoupled light. And now let's assume that these molecules bind to the sensor surface. So what happens, it locally changes the refractive index because the molecules have a different refractive index than the surrounding water. So what happens, it changes the angle of incidence, or not incidence, but the coupling angle. So if these molecules bind, this detector signal over here shifts over here. And what we are tracking in the measurement, which is interesting for the sensorgram for the chemist, biologist, is this binding signal over here. So that's the peak position over time. So if I go back quickly, you see it shifts, and now this is the amount with how much is bound to the sensor surface. And let's say we have a rinsing step, we can see that the signal decreases. So going back to the first slide that I showed you, another big advantage of this system of label-free measurements, it's a continuous measurement. So we can, as I said, the mirror is oscillating at 1 kilohertz, but normally we write down the measurement every second. So you have actually a continuous measurement, and not only like in fluorescent assays, there are some, but normally you have an endpoint signal. You only know how much, for example, has bound. But here you can also deduce the association and dissociation constants of your signal. So you don't only know how much is bound, but you also know about the kinetics of your reaction. So this is in detail the sensor that we are using at the moment. So we have in-coupling and out-coupling grating. The grating period is half a wavelength of the intergrating wavelength, more or less at 360 nanometers. It's actually not to scale, so the grating depth is only around 10, 20 nanometers. And this AFM image of the chip, and these chips are produced in optics pulses. It's also quite easy to scale them up. So for multiplexed measurements at the moment, we are only measuring it on 8 channels in the center, but you could easily scale it up, as I said. So we started off with a rather big lab prototype, which is not really portable, not really robust, and you cannot really bring it into the field. But we ended now towards the end of the project with a rather small, a little bit bigger than a shoebox-sized system, which is integrated, so all the internal computational power is inside, data acquisition, and we can also hook it up to like a wireless module or GSM, so to transmit the data wirelessly. It's multiplex, so we have 2 reference channels and 6 measurement channels. As I said, it's quite compact, quite low power, so a few watts, so it's not ultra low power or something. It's rather affordable, and there's also the fluidics integrated. It's quite easy to handle. Yeah, there's just other pictures with and without the hood. And before I show you some data on the results, what we did is, I'm a physicist, not biologist, so what I prefer to rule out any effects of the assay or biochemical assay, what's going on the surface. What we normally like to do to compare such systems are just by injection of, let's say, glycerol concentrations, because glycerol is quite a different refractive index than water, and if we mix glycerol with water, we can induce like a refractive index step. So we actually not starting to characterize the system with an assay like this, as I showed you, but we just take water, and then let's say we introduce into the system through the fluidics a 1% glycerol in water solution, which gives rise to a refractive index change of about 0.001. So what we do is then just glycerol, and what we want to see is not like a binding curve, because there's no binding, the glycerol does not bind to the sensor surface, but we want to see such a square function, more or less. So, and then we can evaluate the signal to noise and how the fluidics is working and so on. So when we compared the system we had, the system we had available, in which is like the gold standard on the market, is from Biacore, the Biacore 3000. It's not the newest, but still a very good instrument. And so we did these glycerols injections on the Biacore and also on the Argo system, so the signal to noise looks fairly similar. And I mean, I need to say that this system is, yeah, like little fridge sized, and it costs quite a lot. I guess starts in 300 UK or something. And also here we compare, so the long-term stability is also important if you want to measure in the field and for monitoring purposes over a longer time. So I compare it here with 3 systems. So again, a glycerol injection for the Biacore system. Unfortunately, I don't have longer data here, but the green one, it's the newest version of our Argo system, and also over 1 or 2 hours the system just stays nice and stable. Also regarding the noise, so the old system that I showed you was still a little bit noisy, but the newest version is stable and in the noise region of the Biacore, I'd say. Also regarding linearity, so we can cover quite a big dynamic range, several orders of magnitude in the refractive index perspective, and it's highly linear, and also the limit of detection, it's around 3 to 10 to the minus 7th effective refractive index units. As I told you, I'm not, because in the morning we've seen much about the biology and the assay which is performed on the system, but I just wanted also to show you that it's actually, we're able to also do not just the glycerol injections, which might be interesting for a physicist, but not really for a biologist, but we are able to also do and perform normal assays on the system, and also here it's an example that has been done at Rickhild Institute from Wilhelm Hasnot and Adil Buslin, also to compare with a standard assay that they have, that the system is, gives comparable results to the Biacore 3000. So in summary, I guess we came up with this Argos, the angle interrogated optical sensor, which is a rather integrated label-free optical biosensor. It's versatile. It's not only applicable for this very project. You could also use it in any lab, or for the pharmaceutical industry, or in food feed monitoring and so on, wherever you can have surface bound reactions, or where you normally use a SPR system. It's multiplexed, as I said. We have 8 channels, 6 measurement channels and 2 reference channels in the system. You could quite easily scale them up. It has a rather high sensitivity and stability. It's affordable. It's several times, magnitudes almost, cheaper than a Biacore system. It's compact and relatively low power, so it uses just, or it needs just a few watts, so you could actually do some measurements in the field. These are the acknowledgements, of course, the entire radar consortium, but also people at CSCM, Optics Pulses, and my advisor at ETH that I want to thank. Thank you also for your attention, and if you have any questions, just go ahead.
Does anyone have any questions for Florian?
I have a question.
Yeah.
What I'm going to ask is maybe obsolete, okay?
Mm-hmm.
But I know that Viacor was very aggressive several years ago with their patent against other companies. Don't you have intellectual property issues to patent Viacor there?
No, I don't think so. So we also have, based on earlier methods that has been developed also in the past at CSCM, so we also have a certain patent portfolio, and so far, so we haven't been in any patent issues so far. But I'm happy that I, as a PhD student, I don't need to fight with these things at the moment, at least. But maybe Stefan knows whether it's completed. Because SPR is based on a, as you probably know, on a gold surface, so the principle is quite different. I mean, yeah, there's not really something that's overlapping. It's true, it's a very similar, so the measurements that you do are very similar, but the method is different because it's a waveguide-based dielectric measurement. The other one is a plasmonic measurement.
I have a question for Florian, which is that basically your system that you've got, you hopefully will see it going into lots of different sort of applications. But how robust is it? I know that you're only in a prototype situation, but I mean, does it have to sort of be in a very stable setting, or can it be on a boat? You know, I'm not quite sure whether or not if you do a little bit of movement, whether that's going to affect all of the optics.
I guess what would affect it if it's like really vibrating as hell, like a high pitch or a high frequency vibrating. But this is also something that I mean, if you put more engineering effort into it, that could be solved. But just like movements of a boat, like these lower frequency movements, it does not affect it. Yeah, as you said, it's still so the first prototype. So we call this now the pilot series. Yeah. So we hope it's already a little bit more advanced. But yeah, I mean, I think we could even miniaturize it more and make it more handy. But yeah.
And you know, from a commercialisation, you might not know the answer to this, but from a commercialisation viewpoint, is it something that you would hope to see it? Maybe because presumably it would be a lot cheaper than a Viacor machine, that it might be something that you could have not only sort of out in fish farms, but maybe at sort of doctors' surgeries and things like that.
Yeah, exactly. I mean, if anyone is interested, yeah, just contact me. No, we would be really happy if we could spread it out, because I mean, as I said, the Viacor system is 70 kilos, it's huge, it's expensive. You cannot just have it everywhere. So it's like really an investment to have in a bigger laboratory, and we hope that also smaller laboratories are also, as I said, food or water quality monitoring agencies.
World as well, maybe.
Exactly.
Yeah.
So no, for sure, we're hoping that we can.
Okay, thank you very much.
Thanks.
I'd like to thank all the speakers this morning. I think it's been a really interesting set of talks, and go off for coffee now. Thanks a lot.